And we are going to be going over the example question that I asked you when we were going over how intermolecular forces affect properties. And what I did was I gave you guys the boiling points of the 3 different substances that we were talking about in the previous lecture. So methanol here, which is C3OH, has a boiling point of 64.7 degrees Celsius, and then CH2O has negative 19, and CH4 has negative 161.5. So anytime that I am looking at an intermolecular force question where it is asking me about a property, what I need to do is I need to find the thing that has the highest property. So like in this case, this has the highest melting point, okay? Or I'm sorry, boiling point. I could look at the highest heat of vaporization. I could look at the highest heat of fusion, whatever. The one that has the highest property, except for vapor pressure, which we'll talk about in a second, that one's going to have the strongest intermolecular forces. So when I look at these here, I know that this thing here is going to have the strongest intermolecular forces. Conversely, they could ask you a question where they didn't give you the points, and then they ask you to look at the intermolecular forces and tell you which one would have the higher boiling point, melting point, whatever. The one with the stronger forces always has the highest point value, except for vapor pressure. Vapor pressure would be the other way around. So in this case, C3OH would have the lowest vapor pressure because it has the strongest intermolecular forces. But otherwise, it's always the highest one. So I want to explain why this is the highest boiling point here. If I look, I have the ability to hydrogen bond, I have dipole to dipole interactions, and I have London dispersion forces. Compared to these guys, which are roughly the same size if we look at them, so they're pretty much the same size. We don't have this huge molecule or anything like that. But this one only has London dispersions, and CH2O only has dipole to dipole and London dispersion forces. So what happens is when we're talking about molecules that are roughly the same size, they don't have vastly different molecules, big atom differences or anything like that, what's going to happen is the one that has the greater intermolecular forces are going to have the higher boiling points, whatever. And the big tip off here is hydrogen bonding. Hydrogen bonding is the strongest one by far. So what we need to discuss in our explanation is what's causing this to happen. So what I'm going to say is that the boiling point of CH3OH is higher than CH2O and CH4. Sorry, need to take a drink. So it's higher than those two because it has the strongest intermolecular forces. And I'm just going to put IMFs there because I don't feel like writing intermolecular forces. That is not enough information to earn the points on this question. So this maybe would get you a point, but probably not. So what I have to do then is explain what I'm talking about. So what I'll say is that CH3OH has the ability to hydrogen bond while the others cannot. Okay, that's part of the answer. The second part is going to say hydrogen bonding is the strongest IMF when comparing molecules of the same size. Because CH3OH has the ability to hydrogen bond it should have a higher boiling point. Okay, so what we're doing in all these responses is we are talking about what we predict to happen or what causes the thing we're talking about, and then what about that trend causes that. So what I mean by that is it says, oh, I mentioned that this has the ability to hydrogen bond, and that's great. But the second part and where I earn the credit on these explanations is saying why that's important. So, okay, great, this can hydrogen bond. What does that mean? Well, hydrogen bonding is the strongest intermolecular force, so it should have a higher boiling point because the other ones don't have that. So we're always looking for kind of that second explanation. The reason why I always compare things of the same size is because you will actually see situations where, and I don't have one off the top of my head, but like let's say I have a compound like this. Okay, so it's big, it's beefy. I'm going to keep adding hydrogens. And let's imagine that these are all H's all the way around to fulfill the octet rule for all these carbons. This molecule here is only going to have London dispersion forces in it. However, because of its size and because it's so substantial, it is possible that its London dispersion forces are actually stronger than something that can dipole to dipole interact or something that can hydrogen bond. So it is entirely possible that you will have big molecules that can only have London dispersion forces have properties that are higher. And the trick is that you always need to look at the numbers. So again, if I look at these numbers here, the higher boiling point, the higher heat of vaporization, all that kind of stuff lead always to the thing with the stronger intermolecular forces. So, and I'm totally just making this up off the top of my head. I do not know what this is, but let's say this has a boiling point of 85 degrees Celsius. That tells me, in this case, that the hydrogen bond in CH3OH isn't making a big enough difference to overcome the differences in these London dispersion forces. So in this molecule, because this has a higher boiling point, I know that the London dispersion forces in here are still stronger than the hydrogen bond here because these temperatures give me that data. Okay, so you've got to be very careful when you go through these. What we're going to do is we're going to do a ton of practice with intermolecular forces. The next thing we're going to do is an activity where you guys are going to be taking a look at some chemical properties and paying attention. We're going to be doing some drawing with them, and so we'll get things cleared up. All right, if you have any questions, let me know. Otherwise, good luck.